13.8 billion years ago, in a fraction of a second too small to measure, the entire universe burst into existence from something smaller than a single atom. That moment, the Big Bang, changed everything. It set in motion the expansion of space itself, the birth of stars, galaxies, and ultimately us. But how could everything we know, the vast cosmos, the swirling nebulae, even the ground beneath our feet, come from something so unimaginably tiny? That's the mystery we're about to unravel. Picture this: a universe so dense and hot that matter as we know it couldn't even exist. Atoms hadn't formed yet. Light couldn't escape. Time and space were tangled together in ways that defy our everyday understanding. Then, in an instant, it all exploded outward, creating the fabric of reality as we know it. This isn't just a scientific theory, it's the story of our origins, the answer to why we're here at all, and the evidence for it is written across the night sky, in the faint glow of radiation left over from that colossal birth. But the Big Bang isn't just about what happened billions of years ago. It's about the questions that still haunt us today. What came before it? Could there have been other universes? And what does it mean for the future of everything? Over the next few minutes, we'll journey through the most groundbreaking discoveries in cosmology, meet the brilliant minds who pieced this puzzle together, and confront the mysteries that even modern science can't yet solve. This isn't just a story of the past, it's an ongoing adventure, one that challenges us to rethink our place in the cosmos. So buckle up, we're about to travel back to the very beginning of time itself. The idea that the universe had a dramatic beginning wasn't always obvious. For centuries, many scientists believed the cosmos was eternal and unchanging until a few key discoveries turned that view upside down. In the early 1900s, astronomers were locked in a debate between two competing ideas. On one side, the steady-state theory claimed the universe had no true beginning or end, with new matter slowly appearing to fill the gaps as space expanded. It was elegant, timeless, and ultimately wrong. On the other side, a radical new idea was taking shape, that the universe wasn't static at all, but stretching outward from an explosive origin. The turning point came in 1929 when Edwin Hubble made a staggering observation. Peering through the massive telescope at Mount Wilson Observatory, he noticed something strange about the light from distant galaxies. The farther away they were, the more their light shifted toward the red end of the spectrum, a telltale sign they were racing away from us. This wasn't just random motion. The entire universe was expanding like dots on an inflating balloon. If everything was moving apart now, then tracing time backward meant there had to be a moment when it all began, a single, unimaginably dense starting point. But it was Georges Lemeter, a Belgian physicist and Catholic priest, who connected the dots most boldly. In 1931, he proposed the universe began as a primeval atom, a tiny hot speck that shattered into existence, unleashing space and time itself. At first, even Einstein dismissed the idea, calling it abominable. But Lemeter wasn't just theorizing, he was using the math of general relativity to predict what we now call the Big Bang. And as more evidence piled up, like the discovery of cosmic microwave background radiation, the faint afterglow of that initial explosion, the skeptics slowly fell silent. What's fascinating is how much resistance the Big Bang theory faced before becoming the cornerstone of modern cosmology. It challenged long-held beliefs about an eternal universe, even making some scientists uncomfortable with its philosophical implications. But science doesn't care about comfort, it follows the evidence. And the evidence, from Hubble's galaxies to the whispers of ancient radiation, all points to one inescapable conclusion: our universe had a birthday. Albert Einstein's theory of general relativity didn't just revolutionize our understanding of gravity, it rewrote the rules of the cosmos itself. In 1915, his equations revealed something astonishing. Space and time weren't just a static stage for the universe to play out on. They could stretch, bend, and even evolve. At first, even Einstein didn't grasp the full implications of his own work. When his calculations suggested the universe might be expanding or contracting, he resisted. The prevailing belief at the time was that the cosmos was eternal and unchanging, so he tweaked his equations by adding a fudge factor, what he called the cosmological constant, to force the universe into a static, unchanging state. Years later, when Hubble's observations proved the universe was indeed expanding, Einstein realized his mistake. He famously called the cosmological constant his greatest blunder, though ironically, modern cosmology has since resurrected the idea in a different form to explain dark energy. What's remarkable is that Einstein's original equations, without any adjustments, had already predicted cosmic expansion more than a decade before Hubble peered through his telescope. The math was there all along, hiding in plain sight. This tension between theory and observation reveals something profound about how science works. Even the greatest minds can be blinded by assumptions. Einstein's reluctance to accept an expanding universe wasn't about flawed math, it was about human bias. The idea of a dynamic, evolving cosmos clashed with centuries of philosophical belief in a steady, unchanging reality. Yet once the evidence became undeniable, science corrected course. That's the beauty of the scientific process. It's self-correcting, always inching closer to the truth, even when it means overturning deeply held convictions. The real twist in this story: Einstein's equations didn't just hint at expansion, they pointed toward something even more radical. If the universe is growing larger today, then rewinding time means everything was once compressed into an unimaginably hot, dense state. Lemeter took that idea and ran with it, proposing what we now call the Big Bang. So in a way, Einstein's theory planted the seeds for our modern understanding of cosmic origins, even if he didn't live to see all the evidence pile up. It's a humbling reminder that sometimes the math sees the future before we do. Sometimes the biggest discoveries in science happen by accident. That's exactly what occurred in 1965, when two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were troubleshooting a persistent hiss in their antenna. No matter where they pointed it, this annoying static wouldn't go away. They even cleaned out pigeon nests and droppings, thinking that might be the cause. But the noise remained, a faint, uniform whisper coming from every direction in the sky. What they'd stumbled upon wasn't a technical glitch. It was the oldest light in the universe, the cosmic microwave background, the cooled remnant of the Big Bang's fiery birth. This faint glow is like a cosmic fossil, a snapshot of the universe when it was just 380,000 years old. Before that moment, the universe was so hot and dense that light couldn't travel freely. It was a swirling soup of particles and energy. But as space expanded and cooled, protons and electrons finally combined to form neutral hydrogen atoms, allowing light to break free for the first time. That ancient light, stretched and diluted over billions of years of cosmic expansion, is what we now detect as microwave radiation, a chilly 2.7 degrees above absolute zero. What makes the cosmic microwave background so extraordinary isn't just its age. It's the story it tells about the early universe. When scientists mapped this radiation with incredible precision using satellites like COBE and Planck, they found tiny fluctuations, regions slightly hotter or colder than average. These imperfections are cosmic gold. They're the seeds from which all structure in the universe grew, the slight overdensities where gravity would eventually pull matter together to form galaxies and clusters. Without those tiny variations, the universe would be a featureless sea of particles, and we wouldn't exist. The CMB doesn't just confirm the Big Bang theory, it lets us peer into the universe's infancy with stunning detail. By studying its patterns, cosmologists can calculate the universe's age, composition, and even how fast it's expanding. It's like finding a faded, cosmic fingerprint left behind in the first moments of creation. And perhaps most mind-bending of all, that static on your old analog TV, about 1% of it comes from this primordial light, a whisper from the dawn of time itself. The first second after the Big Bang was unlike anything we can imagine, a chaotic, explosive transformation where the laws of physics as we know them were being forged in real time. Picture a universe so hot that temperatures soared above 10 trillion degrees, a seething ocean of pure energy where particles flashed in and out of existence faster than the blink of an eye. In this frenzy, even the building blocks of matter, quarks and gluons, couldn't hold themselves together long enough to form protons or neutrons. Instead, they zipped around freely in what scientists call a quark-gluon plasma, a state so extreme it can only be recreated momentarily in powerful particle colliders today. But the most dramatic change happened in less time than it takes to snap your fingers. Within a fraction of that first second, the universe underwent a mind-boggling growth spurt known as cosmic inflation. Space itself expanded faster than the speed of light, stretching from smaller than a single atom to the size of a grapefruit in mere moments. This wasn't just rapid expansion, it was exponential, like blowing up a balloon to the size of Earth in an instant. And as space ballooned, it carried with it the seeds of everything to come, tiny quantum fluctuations that would later become galaxies, stars, and planets. During this explosive beginning, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were still unified, acting as one superforce. But as the universe cooled, they began to separate, like ingredients settling out of a cosmic soup. First, gravity peeled away, then the strong nuclear force, which holds atomic nuclei together. Finally, electromagnetism and the weak force split, completing what physicists call the electroweak symmetry breaking. Each of these splits released enormous energy, further shaping the newborn universe. What's astonishing is how precise these early moments had to be for our universe to turn out the way it did. If inflation had lasted just a tiny bit longer, matter would have been spread too thin for galaxies to form. If the forces had separated at slightly different energies, atoms might never have stabilized. Even the slightest tweak to these initial conditions could have left us with a lifeless void instead of a cosmos teeming with complexity. It's as if the universe threaded the narrowest possible needle, and we're the result. Scientists pieced together this story by combining cutting-edge particle physics with observations of the cosmic microwave background. Experiments like the Large Hadron Collider recreate fractions of these extreme conditions, while telescopes capture echoes of that primordial expansion. Together, they reveal a universe that transformed itself from a scorching, formless fireball into a structured, dynamic cosmos, all within the time it takes you to draw a single breath. The universe didn't stay a chaotic soup of quarks and energy forever. As it expanded and cooled, something remarkable happened. The first stable matter began to take shape. Within those first few minutes, temperatures dropped enough for quarks to finally stick together, forming protons and neutrons. These particles didn't just float around aimlessly, they started combining in precise ways, like cosmic Lego bricks snapping into place. This process, known as Big Bang nucleosynthesis, was the universe's first chemistry experiment, and it set the stage for everything that followed. For about 17 minutes, the conditions were just right for protons and neutrons to fuse into atomic nuclei. Most of them paired up to form helium, while single protons remained as hydrogen. Trace amounts of lithium and beryllium also appeared, but that was it, no heavier elements yet. This might sound simple, but the precision of this process is staggering. If the universe had cooled even slightly faster, neutrons wouldn't have had time to combine with protons, leaving us with a universe full of hydrogen and almost nothing else. If it had cooled slower, nearly all the hydrogen would have been converted into helium, leaving stars without their primary fuel. The balance was so delicate that even a tiny shift would have rendered the cosmos lifeless. What's incredible is how much we can predict about this era. Using the known laws of nuclear physics, scientists can calculate exactly how much helium should have been produced in those early minutes. And when they compare their predictions to actual measurements of ancient gas clouds, the numbers match almost perfectly. It's like finding a recipe written in the stars, one that confirms our understanding of the universe's earliest moments. But here's the catch: these newborn nuclei were still naked, lacking the electrons needed to become full-fledged atoms. The universe was still too hot and energetic for electrons to settle into orbit around them. That wouldn't happen until much later, when temperatures cooled further. Still, this was a pivotal step, the moment when the raw ingredients for future stars, planets, and even life itself were forged. Every atom in your body, every molecule in the air you breathe, traces its lineage back to this fleeting window of cosmic alchemy. The simplicity of these first elements hides their profound importance. Hydrogen and helium might seem basic, but they're the universe's ultimate building blocks. Gravity would later pull them together into vast clouds, igniting the first stars and lighting up the darkness. Those stars, in turn, would forge heavier elements in their cores, scattering them across space when they exploded. Over billions of years, this cycle transformed a universe of hydrogen and helium into one rich with carbon, oxygen, iron, and all the other elements essential for planets and life. So while Big Bang nucleosynthesis only produced the lightest elements, it was the crucial first step in a chain reaction that led to galaxies, solar systems, and ultimately, us. Without those 17 minutes of nuclear fusion in the infant universe, the cosmos would have remained forever barren. It's a humbling thought that the very atoms we're made of were crafted in the furnace of creation itself, billions of years before Earth even existed. The Big Bang gave us the universe, but there was a problem: gravity didn't add up. Galaxies were spinning so fast that their visible stars and gas should have flown apart, yet something invisible was holding them together. That's where dark matter enters the story, a ghostly substance that doesn't emit, absorb, or reflect light, yet exerts an undeniable gravitational grip on everything around it. Think of it like the wind: you can't see it, but you feel its force pushing against you. Without dark matter's hidden scaffolding, galaxies would have torn themselves apart long ago, and the cosmos as we know it wouldn't exist. The first clues emerged in the 1930s, when astronomer Fritz Zwicky noticed something bizarre about the Coma galaxy cluster. The visible mass of its stars was far too little to account for the gravity needed to keep the cluster intact. He called this missing ingredient Dunkel Materie, dark matter, but his ideas were largely ignored for decades. It wasn't until the 1970s that Vera Rubin's groundbreaking work on galaxy rotation curves proved Zwicky right. She found that stars at the edges of galaxies orbited just as fast as those near the center, defying Newton's laws unless some invisible mass was holding them in place. The implications were staggering. Up to 90% of a galaxy's mass was completely unseen. So what is dark matter? The leading theory suggests it's made of WIMP, weakly interacting massive particles, hypothetical entities that barely interact with normal matter except through gravity. They're like cosmic ghosts passing through Earth and even our bodies by the billions every second without a trace. Yet despite decades of searching, no experiment has definitively caught one. Alternative ideas propose that dark matter might not be particles at all, but rather primordial black holes left over from the Big Bang, or even flaws in our understanding of gravity itself. What's undeniable is dark matter's role in shaping the universe. Supercomputer simulations show that without its gravitational pull, the slight density fluctuations in the early universe wouldn't have grown into the vast cosmic web of galaxies and voids we see today. Dark matter acted like an invisible scaffold, gathering normal matter into its gravitational wells, where gas could cool and ignite into stars. It's the reason we have galaxies, clusters, and ultimately planets. Yet the mystery deepens. Recent observations of dwarf galaxies and colliding galaxy clusters reveal puzzling inconsistencies in how dark matter behaves, hinting that our models might be missing something fundamental. Some scientists even speculate that dark matter could interact with itself in ways we haven't yet detected, adding yet another layer of complexity. One thing certain, unlocking its secrets would rewrite our understanding of the cosmos, revealing hidden chapters in the story that began with the Big Bang. Until then, it remains one of physics' most tantalizing enigmas, a silent architect of the universe, hiding in plain sight. Just when scientists thought they had the universe figured out, it threw them another curveball. In the late 1990s, two independent teams of astronomers were studying distant supernova, exploding stars so bright they can outshine entire galaxies. These cosmic beacons act like mile markers, helping measure how fast the universe has expanded over time. But their measurements revealed something that defied all expectations. Instead of slowing down as predicted, the expansion of the universe was speeding up. It was as if an unseen hand was giving space itself an extra push, stretching galaxies apart faster and faster with each passing moment. This discovery turned cosmology upside down. For decades, the prevailing assumption was that gravity, the relentless pull of all matter in the cosmos, would eventually slow the universe's expansion, perhaps even reverse it in a dramatic Big Crunch. But the data told a different story. Something was overpowering gravity on the largest scales, driving an acceleration so precise that scientists could calculate its strength to several decimal places. They called this mysterious force dark energy, and it makes up about 68% of the universe's total energy content. To put that in perspective, all the stars, planets, gas, and even dark matter combined account for less than a third of what's out there. The rest pure mystery. So what could dark energy be? The leading explanation points to Einstein's old cosmological constant, a kind of energy inherent to empty space itself. According to quantum physics, a vacuum isn't truly empty. It's seething with virtual particles that flicker in and out of existence. These fleeting fluctuations might generate a repulsive force that counteracts gravity, causing space to stretch at an ever-increasing rate. But there's a catch. When physicists calculate how much energy this quantum vacuum should produce, the numbers are off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the worst mismatch between theory and observation in all of science. Alternative theories suggest dark energy might not be constant at all. Some propose it's a dynamic field, like an invisible fluid filling the cosmos, whose strength changes over time. Others entertain even wilder ideas, that we're seeing hints of extra dimensions or modifications to Einstein's theory of gravity itself. What's certain is that dark energy's effects are subtle but relentless. Unlike dark matter, which sculpts galaxies through gravity, dark energy operates on the vast emptiness between them, stretching the fabric of spacetime so gradually that its impact only becomes obvious across cosmic timescales. The implications are profound. If dark energy continues unchecked, the universe's expansion will eventually pull galaxies so far apart that future civilizations might look up at an empty sky, their neighboring stars and galaxies vanished beyond an unreachable horizon. Distant galaxies will fade from view, their light stretched into undetectable infrared whispers. New stars will stop forming as gas clouds grow too diffuse to collapse. The cosmos will grow colder, darker, and lonelier, a fate cosmologists call the Big Freeze. Yet for all its strangeness, dark energy might hold clues to an even deeper truth. Some theorists speculate it could be linked to the same process that triggered cosmic inflation in the universe's first moments, a kind of echo of creation itself. Others wonder if multiple universes with different dark energy strengths exist, and we just happen to live in one where the value allows galaxies and life to form. Whatever the answer, one thing is clear: the universe still has surprises up its sleeve, and the story that began with the Big Bang is far from over. One of the most puzzling features of our universe is how remarkably uniform it appears. No matter which direction we look, whether toward distant galaxies or the faint glow of the cosmic microwave background, the temperature and structure of the cosmos are almost identical everywhere. At first glance, this shouldn't make sense. Regions of space billions of light years apart have never been in contact with each other, so how could they possibly reach the same conditions? It's like walking into 100 different bakeries across the globe and finding every single loaf of bread baked at the exact same temperature, down to the decimal. The answer lies in an extraordinary idea called cosmic inflation, proposed in the early 1980s by physicist Alan Guth. This theory suggests that the newborn universe underwent a mind-bending growth spurt, expanding faster than the speed of light in a fraction of a second. We're talking about a scale so small and a duration so brief that the numbers barely make sense, from a tiny speck smaller than a proton to something about the size of a grapefruit, all within 10 to the power of -32 seconds. This wasn't just rapid expansion, it was exponential, like blowing up a balloon to the size of the solar system in the blink of an eye. What's revolutionary about inflation is how it solves the uniformity problem. Before this explosive stretching, the entire observable universe was crammed into a microscopic region where temperatures and densities could easily even out. Then, in an instant, inflation magnified this tiny, smooth patch to cosmic proportions, effectively ironing out any irregularities. The wrinkles in spacetime were stretched so thin that they became nearly invisible, leaving behind the remarkably even cosmos we see today. But inflation did more than just smooth things over. It also planted the seeds for all future structure in the universe. Quantum fluctuations, those tiny ripples in energy at the smallest scales, were stretched to astronomical sizes during inflation. These minuscule variations became the blueprints for galaxies, clusters, and the vast cosmic web we observe. Without them, gravity would have had nothing to work with, and the universe would have remained a featureless void. The evidence for inflation is written in the cosmic microwave background, where satellites like Planck have detected the faintest temperature variations just 1 part in 100,000. These match predictions almost perfectly, like finding a fossil from the universe's first moments. Yet inflation remains one of cosmology's most debated ideas. Some scientists argue it's too flexible, capable of explaining almost any observation after the fact. Others propose rival theories like bouncing cosmologies or cyclic universes. What's undeniable is how inflation reshaped our understanding of cosmic origins. It transformed the Big Bang from a singular explosion into something far richer, a dynamic, evolving process with phases and transitions. And perhaps most astonishingly, it suggests that what we call the observable universe might just be one tiny bubble in an unimaginably vast multiverse, where other regions underwent their own inflationary bursts. If true, our cosmic story is even grander and stranger than we ever imagined. The Big Bang theory dominates modern cosmology, but it's not the only explanation for how the universe began. Some scientists argue that our cosmic origin story might be far stranger or even cyclical. Take the bouncing universe model, for example. This idea suggests that instead of a singular explosive beginning, the cosmos undergoes endless cycles of expansion and contraction. Picture a cosmic accordion collapsing inward until it reaches a point of maximum density, then rebounding outward in a new Big Bang. No definitive beginning, no final end, just an eternal loop of creation and destruction. Proponents point to quantum gravity theories, which propose that at extremely high densities, repulsive forces could halt a collapsing universe and trigger a bounce. It's an elegant solution to the singularity problem, avoiding that perplexing moment of infinite density at the start of the Big Bang. Then there's the holographic principle, a radical idea born from string theory. It suggests that our three-dimensional universe might actually be a projection of information encoded on a two-dimensional surface at its boundary, like a cosmic version of a hologram on a credit card. If true, the Big Bang wasn't the birth of a volumetric cosmos, but the moment this holographic screen flickered to life. While this sounds like science fiction, it emerges from serious math, offering potential answers to black hole paradoxes and the nature of space-time itself. The catch: no experiment has yet found evidence to confirm it, leaving the idea tantalizing but unproven. Cyclic models take a different approach, proposing that our universe is just one page in an infinite cosmic flipbook. In these scenarios, colliding higher dimensional brains, think of them as membranes floating in a larger space, could generate Big Bang-like events repeatedly. Each collision births a new universe with slightly different physical constants, creating a multiverse where diversity is the norm. These theories gain traction because they might explain fine-tuning mysteries. If countless universes exist with random laws, it's no surprise we find ourselves in one where conditions permit life. So why does the Big Bang still reign supreme? For all their creativity, alternative theories share a common hurdle: hard evidence. The cosmic microwave background, the abundance of light elements, and the observed expansion of the universe all align with Big Bang predictions with astonishing precision. Meanwhile, rival ideas often rely on phenomena beyond current detection: extra dimensions, pre-Big Bang phases, or unobservable sibling universes. That doesn't make them wrong, just harder to test. The Big Bang's real strength lies in its adaptability. It's been refined for decades, incorporating inflation, dark matter, and dark energy to explain new discoveries, evolving alongside our growing understanding of the cosmos. Yet the search for alternatives isn't pointless. Every challenge to the Big Bang pushes scientists to ask sharper questions, refine their models, and dig deeper into the unknown. Whether our universe had a single beginning or is part of an endless cycle, one thing's certain: the final chapter of cosmic origins hasn't been written. And that's what makes this mystery so thrilling: the possibility that the next great discovery could rewrite everything we think we know. Cosmology has a problem, one that's keeping scientists up at night. When we measure how fast the universe is expanding today using nearby galaxies and supernova, we get one number. But when we calculate it based on the cosmic microwave background, the afterglow of the Big Bang, we get a different, noticeably smaller value. This mismatch isn't just a minor hiccup, it's a full-blown crisis called the Hubble tension, and it threatens to upend our understanding of cosmic evolution. The contradiction is stark. Measurements using Cepheid variable stars, cosmic lighthouses whose brightness pulses at a rate tied to their true luminosity, suggest the universe is expanding at about 73 kilometers per second per megaparsec. Meanwhile, the Planck satellite's analysis of the CMB pegs that number closer to 67. That gap might seem small, but in the hyper-precise world of cosmology, it's enormous. It's like two clocks, both supposedly perfectly calibrated, ticking at stubbornly different speeds. Either we're missing something in our measurements, or the universe has been hiding a fundamental secret all along. Some scientists argue the tension might stem from overlooked errors. Maybe Cepheids aren't the flawless distance markers we thought, or perhaps interstellar dust is skewing supernova measurements. But after years of cross-checking, recalibrating instruments, and inventing new observational techniques, the discrepancy refuses to vanish. That's led many to consider a far more exciting possibility, that we're glimpsing cracks in our standard model of cosmology, hints of physics beyond Einstein's relativity and the known particles. One tantalizing idea involves dark energy, that mysterious force accelerating the universe's expansion. What if its strength isn't constant, as Einstein's cosmological constant assumes, but changes over time? A slight tweak to its behavior in the early universe could reconcile the conflicting expansion rates. Others speculate about early dark energy, a hypothetical field that briefly surged during the cosmos's first few 100,000 years, subtly altering how structures formed. Then there's the radical notion that dark matter interacts with itself in ways we've yet to detect, throwing off our calculations of how galaxies cluster. The stakes couldn't be higher. If the Hubble tension points to new physics, it could redefine everything from the fate of the cosmos to the very nature of gravity. Already, teams are racing to test these ideas with next-generation telescopes like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope, which will map millions of galaxies with unprecedented precision. Whether the solution lies in revised measurements or revolutionary theories, one thing's certain: the universe is nudging us toward a deeper truth, and cosmologists are listening. What if our universe isn't the only one? Imagine a cosmic kaleidoscope where every twist creates a new reality, some with stars and planets like ours, others where gravity repels or time runs backward. This isn't science fiction. It's the Multiverse Hypothesis, a daring extension of the Big Bang theory that suggests our universe might be just one bubble in an endless froth of parallel realities. The idea emerges from the math of cosmic inflation, which predicts that once inflation starts, it never truly stops. Instead, it spawns pocket universes endlessly, each with its own unique physics. Some might have stronger nuclear forces, making stars burn out in seconds. Others could lack dark energy entirely, collapsing back into oblivion before life ever gets a chance. The multiverse isn't just wild speculation, it's a natural consequence of inflation's runaway expansion. When Alan Guth first proposed inflation, he realized it had a curious property. Quantum fluctuations could cause it to pinch off regions of spacetime, creating isolated universes disconnected from our own. Think of it like a boiling pot of water where steam bubbles form and float away. Each bubble is a self-contained universe, sealed off from the others, expanding within its own space. Over infinite time, this process would generate an unfathomable number of universes, each with random variations in their fundamental constants. String theory, the leading candidate for a theory of everything, adds another layer to this picture. It suggests our universe might be one slice of a higher dimensional reality, like a sheet of paper floating in a stack. other universes could exist millimeters away in dimensions we can't perceive, their particles and forces forever hidden from us. Some versions of this brain multiverse even propose that big bangs occur when these higher dimensional membranes collide, releasing energy that births new cosmic realms. But how could we ever test such an outlandish idea? Surprisingly, there are hints. If our universe once bumped against another, the collision might have left scars in the cosmic microwave background, odd temperature patterns or gravitational wave imprints. Telescopes like Planck have searched for these anomalies, and while none have been confirmed yet, the hunt continues. Other approaches lean on math. If the multiverse exists, the statistical distribution of physical constants across universes should make life-friendly ones like ours vanishingly rare. The fact we're here at all, against absurd odds, might be indirect evidence of a larger cosmic lottery. Critics argue the multiverse is untestable philosophy dressed up as science, a retreat from the hard work of explaining why our universe has its specific laws. But supporters counter that it's the opposite, a bold framework that explains fine-tuning without invoking coincidence or design. After all, if every possible universe exists, it's no surprise we find ourselves in one where conditions allow galaxies, planets, and life. The multiverse doesn't just expand our cosmic address, it reshapes how we think about existence itself. Whether it's real or not, the idea forces us to confront the deepest question of all. In a reality where anything is possible, what does it mean to be this universe? The future of the universe hinges on a single, mysterious force, dark energy. Its behavior holds the answer to whether our cosmos will fade into cold emptiness, collapse in a fiery finale, or face something even more dramatic. Right now, the evidence points toward expansion winning the cosmic tug-of-war. Galaxies are racing apart faster than ever, their light stretched into infrared oblivion as dark energy dominates gravity's pull. If this acceleration continues unabated, we're headed for what cosmologists call the Big Freeze. Picture a universe where galaxies grow so distant that future civilizations will see only darkness beyond their local stars. Gas clouds will become too sparse to form new stars, and those still burning will flicker out one by one. Space itself will stretch until even atoms are torn apart, leaving behind a vast, silent sea of subatomic particles drifting endlessly in the void. But the Big Freeze isn't the only possibility. If dark energy weakens over time, or worse, reverses into an attractive force, gravity could regain control. Imagine the expansion slowing, halting, then reversing as galaxies begin rushing back toward each other. Temperatures would soar as cosmic structures collide, merging into a superheated soup of particles. Space itself would shrink, cramming all matter into an increasingly dense, scorching inferno until in a mirror image of the Big Bang, everything collapses into a singularity. This Big Crunch scenario turns the universe's fate into a cosmic boomerang, where creation and destruction are two sides of the same coin. The most violent possibility, though, is the Big Rip. If dark energy grows stronger over time, its repulsive force could eventually overpower not just gravity but every binding force in nature. First, galaxy clusters would be shredded apart. Then, individual galaxies, stars would be torn from their orbits, planets ripped from their suns. In the final moments, even atoms and atomic nuclei would be split asunder, dissolving all structure into a chaos of disconnected particles. The universe wouldn't just expand, it would disintegrate. What determines which path we're on? It all comes down to dark energy's equation of state, a fancy term for how its density changes as the universe expands. If it remains constant, like Einstein's cosmological constant, the Big Freeze awaits. If it decays, the Big Crunch becomes possible, and if it grows more potent. Brace for the Big Rip. Current observations slightly favor the first scenario, but the margins are slim enough to keep cosmologists questioning. The James Webb Space Telescope and upcoming surveys like the Vera Rubin Observatory are hunting for clues, measuring how dark energy's push has changed over cosmic time. The strangest twist, even if the universe is doomed to expand forever, localized pockets of complexity might persist. Some theories suggest that in a far future universe, intelligent civilizations could harness black holes to survive near indefinitely, extracting energy from their rotation or even creating artificial universes in labs. It's a wild thought that life might outwit cosmic fate, turning the ashes of stars into new beginnings. But for now, the ultimate destiny of everything remains written in the invisible ink of dark energy, waiting for us to decipher its final message. At the heart of the Big Bang lies one of the strangest quirks of nature: quantum fluctuations. These aren't just tiny blips in empty space. They're the universe's way of playing dice with reality itself. According to quantum mechanics, even in a perfect vacuum, particles and antiparticles constantly pop into existence, borrowing energy from nowhere before vanishing again in fractions of a second. It's as if the cosmos has a hidden pulse, a restless energy that defies our everyday intuition. But what if these fleeting flickers didn't just happen inside the universe? What if they created it? Some cosmologists argue that the Big Bang might have been the ultimate quantum fluctuation, an event where uncertainty didn't just tweak the system, but birthed the entire system from scratch. Imagine a primordial void where quantum jitters, normally too small to notice, suddenly got stretched to cosmic proportions. In this scenario, the universe didn't emerge from nothingness in the traditional sense, but from a quantum foam where the very concepts of before and after break down. Time, space, and even causality as we know them might be latecomers to the party, emerging only after this fluctuation ballooned into the cosmos we recognize today. The math behind this idea is as elegant as it is bizarre. Quantum field theory tells us that particles can tunnel through energy barriers they shouldn't classically overcome, like a ball rolling uphill without being pushed. Apply this to the birth of the universe, and you get a scenario where space-time itself could have tunneled into existence from a quantum seed. Some models even suggest that our universe might be one bubble in a frothing multiverse, where countless other bubbles fluctuate into being with different physical laws. It's a humbling thought. The galaxies, stars, and planets we see might all trace back to a microscopic hiccup in the fabric of reality. Support for this idea comes from an unexpected place: cosmic inflation. The same quantum fluctuations that might have sparked the Big Bang also left their fingerprints on the universe's baby pictures, the cosmic microwave background. Those tiny temperature variations we see, they match the patterns predicted by quantum randomness magnified by inflation, like echoes of the universe's first shiver. It's as if the cosmos preserved a snapshot of its own quantum origins, encoded in the oldest light we can observe. Yet the theory isn't without its critics. One major hurdle is the question of what, if anything, existed before the quantum fluctuation. Quantum mechanics famously avoids definitive answers about when or why events happen, dealing in probabilities rather than certainties. Applying it to the origin of everything forces us to grapple with whether before even has meaning in a realm where time itself may be emergent. Some physicists argue that asking what triggered the fluctuation is like asking what's north of the North Pole, a question that dissolves under scrutiny. The beauty of this idea lies in its audacity. It bridges the two most successful yet seemingly incompatible theories in physics: quantum mechanics and general relativity, by suggesting that the universe's grandest structure owes its existence to the tiniest of phenomena. Whether it's the final answer or just a stepping stone, one thing's clear: the quantum origins of the Big Bang remind us that reality, at its core, is far stranger and more wondrous than we ever imagined. Black holes aren't just cosmic vacuum cleaners, they're time capsules, preserving conditions so extreme they rival the universe's first moments. At their cores lies a singularity, a point where gravity crushes matter into infinite density, space and time twist beyond recognition, and the laws of physics as we know them simply break down. Sound familiar? It's eerily similar to the state of the universe an instant after the Big Bang, when all of existence was compressed into a single, unfathomably hot and dense speck. This striking parallel has led some scientists to wonder, could black holes be cosmic laboratories, offering us a glimpse into how everything began? The connection runs deeper than just density. Both scenarios, the birth of the universe and the heart of a black hole, represent boundaries where our current theories fail. General relativity predicts singularities in both cases, but these are really just placeholders for "here be dragons" in our equations. They signal where quantum gravity, a theory marrying relativity with quantum mechanics, must take over. Studying black holes might be our best shot at uncovering those missing rules, the same ones that govern the universe's explosive first moments. Imagine it like reverse engineering a fireworks show by examining the scorch marks left behind, except the scorch marks are the Hawking radiation slowly leaking from black holes, carrying faint clues about their inner workings. One radical idea even suggests that black holes could spawn new universes inside them. The concept, sometimes called cosmological natural selection, proposes that when a singularity forms, the extreme conditions might trigger a new Big Bang, birthing a separate space-time bubble with its own physical laws. In this wild scenario, our entire universe could be the offspring of a black hole in some higher dimensional parent cosmos. While this remains speculative, it's a testament to how deeply these two phenomena might be linked. Yet the most tantalizing evidence comes from entropy, the measure of disorder in a system. Black holes have enormous entropy, hinting at unimaginable complexity hidden beneath their event horizons. The early universe, too, was in a low entropy state, a fact that still puzzles cosmologists. Some theorists argue that understanding black hole entropy could solve this mystery, revealing why the Big Bang's initial conditions were so finely tuned for structure and life. It's as if black holes hold a mirror to the universe's birth, reflecting back answers we're only beginning to decode. Of course, there's a catch. We can't directly observe a singularity inside a black hole or otherwise. But cutting-edge tools like gravitational wave detectors and black hole imaging projects are bringing us closer than ever. Each ripple in spacetime from colliding black holes, each blurry photon ring captured by telescopes like the Event Horizon Telescope, carries subtle hints about gravity's behavior under extreme conditions. By piecing together these clues, we're not just unraveling the secrets of black holes, we're peering back toward the very first tick of the cosmic clock. The irony is poetic. Black holes, once thought to be the universe's ultimate dead ends, might instead be portals to its origins. They challenge us to rethink not just where space and time break down, but where they might have begun. And in that challenge lies an exhilarating possibility that the key to understanding the Big Bang isn't just buried in the distant past, but lurking in the darkest corners of our present cosmos. The hunt for gravitational waves began not with a bang, but with a century-old prediction. In 1915, Albert Einstein's general theory of relativity suggested that massive accelerating objects like colliding black holes or neutron stars should send ripples through the very fabric of spacetime. But Einstein himself doubted we'd ever detect these cosmic tremors. They were simply too faint, warping space by less than the width of an atomic nucleus over thousands of miles. Fast forward to September 14, 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, proved him wrong. For the first time in history, humanity felt the universe shake. The signal that changed everything lasted just 0.2 of a second, a barely perceptible chirp in the data, yet that fleeting wobble told an epic story. It came from two black holes, each about 30 times the mass of our Sun, spiraling toward each other 700 million light-years away. As they merged, they unleashed energy equivalent to 3 suns converted entirely into gravitational waves. The resulting distortion stretched and squeezed Earth's detectors by 1,000th the diameter of a proton, a shift so small it's like measuring the distance to Alpha Centauri, the nearest star system, to within the width of a human hair. That LIGO instruments could catch this whisper from the cosmic depths remains one of engineering's greatest triumphs. But why stop at black holes? Cosmologists now dream of capturing gravitational waves from the universe's very first moments. During cosmic inflation, that explosive expansion in the Big Bang's first sliver of a second, quantum fluctuations in spacetime itself may have generated primordial gravitational waves. Unlike the high-frequency ripples from black hole collisions, these would be ultra-low frequency, with wavelengths stretching across the observable universe. Finding them would be like uncovering a fossilized echo of creation, a direct window into physics at energies 1 trillion times beyond what particle colliders can reach. The challenge: these ancient waves would be buried under eons of cosmic noise. To dig them out, scientists are turning to ingenious methods. Pulsar timing arrays use dead stars as cosmic metronomes, monitoring their ultra-precise radio pulses for subtle timing shifts caused by passing gravitational waves. Space-based detectors like the proposed LISA mission would float lasers millions of miles apart in orbit, free from Earth seismic chatter. And some theorists even suggest looking for imprints these waves left on the cosmic microwave background, like footprints frozen in the universe's oldest light. The stakes couldn't be higher. Primordial gravitational waves could reveal whether inflation truly happened, and if so, what drove it. They might expose hidden dimensions or clues about quantum gravity. Some models even predict signatures from events before the Big Bang, hinting at a cyclical or multiverse cosmology. Every undetected frequency band we search is like turning the dial on a cosmic radio, waiting for static to resolve into the universe's first song. What's astonishing is how far we've come in just a few years. From Einstein's skepticism to LIGO Nobel Prize-winning detection, gravitational wave astronomy has exploded. Future observatories could unveil collisions from the universe's dark ages before stars ignited, or catch the death spirals of supermassive black holes from billions of years ago. But the ultimate prize remains those primordial ripples, the tremors of spacetime's birth. If we find them, we won't just be studying the Big Bang, we'll be listening to it. The Big Bang isn't just a scientific theory, it's a cultural phenomenon popping up everywhere from sitcoms to blockbuster films. But how often does Hollywood get it right? Take the iconic opening of The Big Bang Theory, where galaxies swirl and particles dance to a catchy theme song. While it captures the energetic spirit of cosmic origins, the real Big Bang wasn't an explosion in space. It was the rapid expansion of space itself, a nuance even some of the smartest TV scientists gloss over. Then there's Doctor Who, where the Time Lords supposedly harnessed the power of the Big Bang to reboot the universe. As thrilling as that sounds, the show takes creative liberties. In reality, you can't weaponize the Big Bang. It wasn't a localized event with a center, but the birth of spacetime everywhere at once. Even Star Trek dips into cosmic origins, with episodes featuring alternate universes born from different Big Bang conditions. While these storylines are gripping, they often simplify the mind-bending physics into flashy visuals and dramatic stakes. Movies don't fare much better. The Hitchhiker's Guide to the Galaxy jokes about the universe being created by a supercomputer, while Men in Black famously reveals our entire cosmos is just a marble in an alien's game. These playful takes highlight a deeper truth. The Big Bang is so far outside everyday experience that storytellers often replace its complexity with metaphors, some clever, others wildly misleading. Yet not all portrayals miss the mark. Cosmos, both Carl Sagan's original and Neil deGrasse Tyson's reboot, uses stunning animations to depict inflation and quantum fluctuations with remarkable accuracy. Documentaries like A Brief History of Time weave Stephen Hawking's insights into accessible narratives, showing how science wrestles with the universe's beginnings. Even Interstellar, while focused on black holes, nails the relativity of time, a concept deeply tied to cosmic expansion. The bigger question is, does it matter if pop culture bends the facts? In one sense, no. These stories spark curiosity, drawing millions into astronomy's biggest mysteries. But there's a risk too. When media reduces the Big Bang to a literal explosion or a mystical event, it obscures the real scientific triumphs behind it, the decades of math, observation, and debate that transformed a radical idea into our best explanation of cosmic origins. Perhaps the most fascinating twist is how the Big Bang mirrors storytelling itself. Just as scientists piece together clues from ancient light and distant galaxies, filmmakers and writers reconstruct the universe through imagination and speculation. Both are searching for answers, just with different toolkits. The difference: science demands evidence while fiction thrives on wonder. And in the end, maybe that's the perfect balance. One to teach us how the universe began, the other to remind us why it captivates us so deeply. The Big Bang does more than explain the birth of the cosmos. It forces us to confront questions that have haunted philosophers for millennia. If the universe had a definitive beginning, what, if anything, came before it? The very concept of before stumbles when time itself emerges from that primordial instant. Some traditions, from Christian theology to Hindu cosmology, have long described creation ex nihilo, out of nothing. But modern physics twists this idea into something stranger. Quantum mechanics suggests nothing is never truly empty. Even a vacuum seethes with potential. Could the universe have arisen from this restless quantum foam, a fluctuation frozen into permanence by inflation? The line between physics and metaphysics blurs when we peer too closely at time's vanishing point. This uncertainty fuels heated debates among cosmologists and philosophers alike. On one side are those who argue the Big Bang represents a true beginning, a moment when causality itself was born. They point to the Borde-Guth-Vilenkin theorem, which mathematically suggests any expanding universe with an average positive energy density must have a finite past. In other words, no matter how you tweak the model, classical physics insists there was a start. But others counter with ideas like loop quantum gravity, where the singularity dissolves into a quantum bounce. Here, the Big Bang wasn't a beginning but a rebound from a prior collapsing phase, part of an endless cycle with no first cause. The challenge: both camps grapple with the same limitation. Our laws of physics break down at the singularity, leaving speculation as the only tool. Then there's the anthropic principle, which takes the question of cosmic origins in a startling direction. If the fundamental constants of nature, the strength of gravity, the mass of electrons, were even slightly different, life as we know it couldn't exist. So why does our universe seem so finely tuned? Some argue this points to a multiverse, where countless universes with random constants exist, and we simply inhabit one where conditions allow consciousness. Others see it as evidence of deeper design, though science shies from such teleological leaps. What's fascinating is how the Big Bang, once dismissed as quasi-religious for positing a beginning, now fuels arguments that edge toward philosophy's oldest quandaries. Is our universe purposeful or a glorious accident? These debates ripple beyond academia. The idea that everything, every galaxy, every atom, every thought traces back to a single event reshapes how we perceive our place in the cosmos. It's humbling to think the iron in our blood was forged in dying stars, but even more so to realize those stars owe their existence to quantum ripples magnified by inflation. For some, this vast causal chain evokes awe, for others, existential vertigo. The poet Rainer Maria Rilke once wrote, "You must change your life after glimpsing the sublime." In an age where telescopes show us newborn galaxies and particle colliders recreate the universe's first microseconds, the Big Bang demands a similar reckoning. Perhaps the most profound implication is how it reframes the very nature of reality. If space-time is emergent, not fundamental, then our perception of a steady, linear universe might be an illusion, a useful approximation that crumbles at cosmic extremes. The Big Bang hints that reality could be more like a symphony, where time and space are instruments playing a score we've only begun to decipher. Whether we're alone in this symphony or part of an infinite ensemble remains the greatest unanswered question of all. The Big Bang Theory doesn't just belong to science, it's woven into humanity's oldest stories about where we come from. Across cultures and faiths, creation myths have grappled with the same fundamental question: how did everything begin? What's fascinating is how many of these traditions, while vastly different in detail, share a common thread with modern cosmology, the idea of a universe emerging from a singular, transformative event. Take the Book of Genesis, where the Judeo-Christian tradition describes a formless void before God speaks light into existence. The parallels to the Big Bang's explosive beginning are striking, even if the mechanisms differ. Pope Pius XII famously called the Big Bang scientific evidence for creation, while other Christian theologians see it as a metaphorical echo of divine will, where science reveals the how and faith explores the why. Hindu cosmology offers an even more startling resonance. Ancient texts like the Rig Veda describe a cosmic egg brahmanda hatching to form the universe, a concept that mirrors the singularity from which our expanding cosmos emerged. But Hinduism also introduces cyclical time, with universes endlessly dissolving and reforming, an idea that intriguingly aligns with some modern multiverse hypotheses. Meanwhile, Islamic scholars have long engaged with cosmology. The Quran's description of the heavens as woven together before being split apart has led contemporary Muslim scientists to draw connections to cosmic inflation. These aren't mere coincidences, they reveal how deeply humanity has yearned to understand origins, whether through revelation or equations. Yet tensions arise when science and scripture seem to clash. Some literal interpretations of creation stories, like young Earth creationism, reject the Big Bang's timeline entirely. Others find harmony through reinterpretation, like the day-age theory in Abrahamic faiths, where the days of Genesis symbolize vast cosmic epochs rather than 24-hour periods. Buddhist philosophy takes a different approach, sidestepping the question of a definitive beginning altogether. The Dalai Lama has openly embraced Big Bang cosmology, noting that Buddhism's focus on impermanence and interdependence aligns well with a dynamic, evolving universe. What's remarkable is how these dialogues are evolving. The Vatican Observatory, staffed by Jesuit astronomers, actively researches cosmic origins, blending faith with cutting-edge science. In India, physicists and Vedic scholars hold conferences exploring parallels between quantum vacuum fluctuations and ancient concepts of shunya, void. Even atheist scientists like Stephen Hawking acknowledge the emotional power of creation stories, calling them humanity's first attempt at cosmology. The Big Bang, in this light, becomes a rare bridge, a scientific theory that resonates with the awe and wonder at the heart of spiritual inquiry. These intersections don't erase the differences between science and religion, but they reveal a shared human impulse to stand beneath the stars and ask where it all began. Whether through telescopes or sacred texts, we're all seeking the same truth, just from different paths. And perhaps that's the most profound lesson of all, that the universe's origin story is vast enough to hold both equations and epiphanies, each adding depth to the other. The universe shouldn't exist, at least not as we know it. Every fundamental force, every constant etched into the fabric of reality, from the strength of gravity to the mass of an electron, appears precisely calibrated to allow galaxies, stars, and ultimately, life to emerge. Tweak any of these values even slightly, and the cosmos collapses into chaos. Gravity a bit stronger, stars burn out in millions of years instead of billions, leaving no time for planets or life to evolve. The nuclear force a fraction weaker, hydrogen never fuses into helium, and the universe remains a dark, starless void. This eerie precision is what physicists call fine-tuning, and it's one of the most baffling riddles to emerge from the Big Bang's aftermath. Enter the anthropic principle, a deceptively simple idea with profound implications. It states that the universe must have properties that allow life to arise, because if it didn't, we wouldn't be here to wonder about it. Think of it like a cosmic version of survivorship bias. We're not observing a random universe, but one that necessarily permits observers. The principle comes in two flavors. The weak version is almost a truism. It merely notes that our existence constrains what we can observe. But the strong anthropic principle ventures further, suggesting the universe might be compelled to produce conscious life, as if observers were somehow a built-in feature of cosmic design. Where does the Big Bang fit in? Those first moments set the stage for everything to come. During cosmic inflation, quantum fluctuations were stretched to macroscopic scales, seeding the galaxies we see today. But inflation's energy, duration, and termination had to be exquisitely balanced. Too much expansion, and matter dilutes into nothingness. Too little, and gravity collapses everything back into a singularity. Even the Big Bang's aftermath required precision. The ratio of matter to antimatter, the rate of cosmic expansion, the stability of atomic nuclei, each a razor's edge between a lifeless void and a universe teeming with possibility. Critics argue the anthropic principle is a cop-out, a way to dodge deeper explanations, but supporters counter that it's a legitimate lens for grappling with fine-tuning. Some take it further, proposing a multiverse where countless universes bubble into existence, each with random physical constants. In this vast cosmic lottery, a handful inevitably hit the jackpot, conditions just right for life. We, of course, find ourselves in one of those lucky winners. It's like a puddle marveling at how perfectly its hole fits it, unaware of the countless other puddles and holes that didn't align. Yet the multiverse raises its own questions. If other universes are unobservable by definition, can the idea ever be tested? And why does our universe's fine-tuning extend beyond the bare minimum for life, featuring mathematical elegance and discoverable laws? Some scientists, like Nobel laureate Roger Penrose, calculate the odds of our universe's initial conditions as astronomically improbable, so much so that they hint at deeper principles yet unseen. Others explore radical alternatives, like the simulation hypothesis or the idea that observers somehow retroactively influence the universe's laws. What's undeniable is how the anthropic principle reshapes our cosmic perspective. It turns the universe from a passive stage into an active participant, one where the mere act of observation becomes part of the story. Whether through multiverses, undiscovered physics, or something stranger, this principle forces us to confront a humbling truth. The Big Bang didn't just create a universe. It created a universe that could create us, and that might be the most astonishing fine-tuning of all. For all its explanatory power, the Big Bang theory still leaves us staring into the abyss of unanswered questions. The most glaring one, what or what wasn't there before it all began? The problem isn't just scientific, it's linguistic. The word before implies time, but time as we understand it may have started with the Big Bang itself. Asking what came before is like asking what's north of the North Pole, a question that might not even make sense in the framework of reality. Some theories, like loop quantum cosmology, suggest there was no true beginning, just an eternal cycle of expansion and contraction, with each Big Bang preceded by a big crunch. Others propose a multiverse where our universe is one bubble in an endless froth of cosmic foam, each with its own birth conditions. Then there's the mystery of the singularity, the point of infinite density where the laws of physics break down entirely. General relativity predicts it, but nature abhors infinities. Quantum gravity theories, like string theory or loop quantum gravity, attempt to rewrite this cosmic cliffhanger, replacing the singularity with a quantum bounce or a higher dimensional collision. Imagine the universe not as a fiery explosion from nothing, but as a cosmic phoenix rising from the ashes of a previous universe's collapse. The challenge. Without a theory that unifies quantum mechanics and gravity, these ideas remain tantalizing speculation. Dark energy and dark matter add more layers to the puzzle. We know they dominate the universe's composition, but we still don't know what they are. Dark energy's accelerating push could hint at new physics, or it might mean Einstein's cosmological constant was right all along. Dark matter's invisible grip shapes galaxies, yet decades of searches have failed to detect its particles. Are we missing something fundamental, or are these phenomena shadows of deeper, undiscovered laws? Even inflation, while successful, raises its own questions. What triggered it? Was it a one-time event, or does it happen endlessly across a multiverse? Some models suggest inflation never truly stops, just pauses in pockets like ours, while other regions of spacetime continue inflating eternally. If true, our universe might be a single bubble in an infinite cosmic ocean, forever out of reach from neighboring realities. The biggest shock, these aren't just philosophical musings. Telescopes like the James Webb and future gravitational wave detectors could provide clues. Primordial gravitational waves, for instance, might carry imprints from pre-Big Bang physics, if such a thing exists. The cosmic microwave background's faintest fluctuations could reveal whether our universe collided with another in its infancy. Every unanswered question is a frontier, and the answers, if we find them, might rewrite not just cosmology, but our very understanding of reality. For now, the mysteries remain not as failures of science, but as invitations to look deeper. The quest to unravel the universe's deepest secrets is far from over. In fact, we're on the brink of a new golden age of discovery. Cutting-edge tools are pushing the boundaries of what we can observe, bringing us closer than ever to understanding the Big Bang's most elusive mysteries. Leading the charge is the James Webb Space Telescope, a marvel of engineering designed to peer back over 13 billion years, capturing light from the universe's first galaxies. Unlike Hubble, which sees primarily invisible light, Webb's infrared eyes can penetrate cosmic dust, revealing the faint glow of stars born just a few 100 million years after the Big Bang. Already, it's spotting galaxies so massive and mature that they're challenging our models of cosmic evolution. How could such structures form so quickly? The answers might rewrite our understanding of dark matter's role in the early universe or even hint at exotic physics at play during inflation. But Webb isn't working alone. The Vera Rubin Observatory, set to begin operations in Chile, will map the entire southern sky every few nights with its 3.2 gigapixel camera. By tracking billions of galaxies and supernova, it'll create the most precise 3D map of the cosmos ever made, shedding light on dark energy's accelerating push. Does dark energy's strength change over time? Rubin's relentless scans could reveal subtle shifts, helping us predict whether the universe faces a big freeze, a big rip, or something even stranger. Meanwhile, the Nancy Grace Roman Space Telescope will study cosmic inflation's fingerprints in the distribution of galaxies, searching for patterns that might distinguish between competing theories of the universe's explosive birth. On the ground, particle colliders are simulating the Big Bang's extreme conditions in miniature. The Large Hadron Collider has already recreated quark-gluon plasma, the seething soup of particles that filled the universe's first microseconds. Future upgrades aim to probe even higher energies, potentially uncovering particles or forces that shaped cosmic inflation. Meanwhile, next-generation experiments like the Einstein telescope will listen for gravitational waves from the universe's dark ages, the era before stars ignited. These ripples in spacetime could carry echoes of primordial black holes or even evidence of extra dimensions. Perhaps the most ambitious project on the horizon is the Laser Interferometer Space Antenna, or LISA. This trio of spacecraft, set to launch in the 2030s, will float millions of miles apart, laser beams connecting them like a celestial harp. Unlike ground-based detectors, LISA will sense low-frequency gravitational waves, the kind emitted by supermassive black holes merging at the dawn of time. These waves might encode clues about the universe's first seconds, or even reveal phenomena we haven't yet imagined. The common thread: each of these missions tackles a piece of the Big Bang puzzle from a different angle. Webb peers at ancient light, Rubin tracks cosmic expansion, colliders recreate primordial fire, and LISA listens to spacetime's vibrations. Together, they form a symphony of exploration, each instrument tuned to a different frequency of the universe's origin story. And as the data pours in, one thing becomes clear: the more we learn, the more we realize how much we've yet to discover. The Big Bang isn't just a moment in the past, it's a doorway, and we're only now stepping through. String theory isn't just another idea in physics, it's a radical reimagining of reality itself. At its core, it proposes that the fundamental building blocks of the universe aren't point-like particles but tiny, vibrating strings. These strings oscillate at different frequencies, much like the strings of a violin producing distinct musical notes, and those vibrations determine whether we perceive them as electrons, quarks, or even the force carriers of nature. But here's where it gets mind-bending. For the math to work, these strings can't just exist in the 3 dimensions we're familiar with. They require extra dimensions, possibly 6 or 7, more curled up so tightly that we've never noticed them. This is where the Big Bang enters the picture. One of string theory's most compelling offshoots is the idea of brane cosmology. Imagine our universe as a 3-dimensional membrane, or brane, floating within a higher dimensional space. Nearby, there could be other branes, each hosting their own separate universes with different physical laws. In this scenario, the Big Bang might not have been an explosion from nothing, but a collision between our brain and another. Picture two sheets of paper floating parallel to each other, suddenly smacking together. The energy from that cosmic crash could have ignited the rapid expansion we call the Big Bang, seeding our universe with matter and radiation in the process. Supporters of this ekpyrotic universe model argue it solves some of the Big Bang's thorniest puzzles. For instance, why is the universe so uniform on large scales? If two brains collided smoothly and evenly across their entire surfaces, the energy released would have been distributed uniformly, explaining the cosmic microwave background's remarkable smoothness. It also sidesteps the singularity problem. No need for infinite density when you have a higher dimensional collision as your starting point. But how do we test such an outlandish idea? One clue might lie in gravitational waves. If the Big Bang was indeed a brain collision, it could have produced ripples in space-time with a distinctive signature. Future detectors like the Laser Interferometer Space Antenna might catch these whispers from the universe's birth. Another hint could come from the cosmic microwave background. Certain patterns in its polarization might reveal whether space-time was warped by pre-Big Bang events, like a fingerprint left by higher dimensional physics. String theory's vision of the Big Bang isn't without critics. Some physicists argue it's untestable, a beautiful mathematical framework with no clear path to verification. Others point out that the extra dimensions it requires are purely hypothetical, with no experimental evidence to date. And then there's the sheer complexity. String theory's equations have millions of possible solutions, leading to a landscape of potential universes, only one of which happens to be ours. Yet for all its challenges, string theory offers something profound, a way to unify quantum mechanics and general relativity, the two pillars of modern physics that otherwise refuse to cooperate. In this framework, the Big Bang isn't a singular, inexplicable event but part of a larger, multidimensional dance. Whether it's the true story of our origins remains to be seen, but one thing's certain: it expands our imagination of what the cosmos might be hiding and where our search for answers should look next. Among the countless particles born in the Big Bang's aftermath, few are as ghostly or as revealing as neutrinos. These subatomic phantoms, nearly massless and electrically neutral, zip through the universe at almost the speed of light, barely noticing the planets, stars, or even entire galaxies in their path. 1 trillion neutrinos pass through your body every second, leaving no trace like cosmic specters. But their indifference to matter is precisely what makes them so valuable to cosmologists. While other particles got tangled in the chaos of the early universe, neutrinos sailed straight through, preserving pristine information about conditions just seconds after creation. The Big Bang produced neutrinos in staggering numbers, so many that today they outnumber atoms in the universe by 1 billion to 1. In those first moments, temperatures were so extreme that neutrinos bounced freely, scattering off electrons and quarks like pinballs. But as the universe expanded and cooled, around 1 second after the Big Bang, something pivotal happened. Matter became too sparse for neutrinos to interact with, and they decoupled, streaming freely through space like runners released from a starting block. This moment froze their properties in time, turning them into cosmic snapshots of the infant universe. What secrets do these time capsules hold? For starters, their very existence helps pin down the universe's expansion rate. When neutrinos decoupled, they carried away energy, subtly altering how matter clumped together in their wake. By studying the large-scale structure of galaxies, the cosmic web woven by gravity scientists can detect the faint imprint of these fleeing particles, like shadows cast by invisible dancers. Even more tantalizing is what neutrinos might reveal about the imbalance between matter and antimatter. The Big Bang should have created equal amounts of both, yet we live in a universe dominated by matter. Neutrinos, with their peculiar habit of oscillating between different flavors, might hold clues to this cosmic asymmetry, a puzzle central to our existence. Detecting primordial neutrinos isn't easy. Unlike the cosmic microwave background, which we can observe directly, these relic neutrinos have cooled to just 1.9 degrees above absolute zero over 13.8 billion years. Their energy is so low that even the most sensitive detectors, like the upcoming Ptolemy experiment, face monumental challenges. But if we could catch just a handful, they'd offer a direct window into the universe's first second before protons formed, before light escaped, when reality was a seething forge of raw energy. Neutrinos also challenge our understanding of mass. For decades, physicists assumed they were weightless, until experiments revealed their tiny but non-zero masses. Where does this mass come from? The answer might involve undiscovered particles or even connections to dark matter. Some theories suggest neutrinos could be Dirac fermions, gaining mass through a mechanism different from other particles, while others propose they're their own antiparticles, a property that might explain the matter-antimatter imbalance. Every neutrino detected today is a messenger from the dawn of time, carrying encrypted notes about the universe's most violent and creative moment. They remind us that the Big Bang isn't just a theory written in equations, it's a story still unfolding, etched into the fabric of reality by particles so elusive, they've spent 13 billion years hiding in plain sight. Time has a direction, a one-way street from past to future that feels so obvious we rarely question it. Eggs crack but never uncrack, coffee cools but never spontaneously heats up. This irreversible flow is called the arrow of time, and its origins trace back to the Big Bang's most subtle yet profound gift, entropy. Entropy, in simple terms, is nature's tendency toward disorder. The second law of thermodynamics states that in any closed system, entropy always increases, a rule that gives time its unmistakable forward march. But here's the puzzle. Why was entropy so astonishingly low at the universe's birth? The Big Bang didn't start with chaos. It began with an exquisitely ordered state, a cosmic wound-up spring that's been unwinding ever since. Imagine a deck of cards perfectly sorted by suit and number. That's the low entropy starting point the universe had, and every shuffle since, every star burning, every galaxy colliding has been spreading those cards into messier arrangements. This bizarrely tidy beginning is what makes time's arrow possible. If the early universe had been high entropy, a lukewarm, evenly distributed soup of particles, there'd be no driving force for change, no way to distinguish past from future. The fact that we remember yesterday but not tomorrow, that cause precedes effect, all hinges on that initial state. Physicist Sean Carroll likens it to a bottle of ink dropped into a swimming pool. The moment it shatters, the Big Bang is the point of lowest entropy, and the ink's inevitable spread into the water mirrors the universe's journey toward disorder. But why did the universe start this way? Some theorists point to cosmic inflation. The rapid stretching of spacetime in the first fraction of a second may have reset entropy to near zero, like ironing out wrinkles in a crumpled sheet. Others propose deeper answers tied to quantum gravity or even the multiverse. In one provocative idea, called the past hypothesis, our low-entropy Big Bang wasn't random, but the result of time-symmetric physics, a universe where entropy is low at both ends, like an hourglass with narrow necks at the top and bottom. From the middle, time would appear to flow outward in both directions, with observers in each half perceiving their own arrow. The arrow of time isn't just a cosmic curiosity, it's the reason complexity exists. Stars shine because they're dissipating energy, planets form because gravity clumps matter unevenly, and life itself thrives on entropy's gradient, like a mill wheel turning in a flowing stream. Without that initial order, the universe would be a featureless equilibrium, timeless in the bleakest sense. Even black holes, those infamous destroyers of information, play by entropy's rules, their event horizons hiding disorder so extreme it defies classical physics. Yet mysteries remain. Why does quantum mechanics, the framework governing particles, seem indifferent to time's direction? At microscopic scales, equations work equally well forward or backward, suggesting time's arrow emerges from statistics, not fundamental laws. And what about consciousness? Some philosophers argue our perception of time's flow is intertwined with entropy, a side effect of brains processing information in a universe with a built-in past and future. The Big Bang's greatest legacy might be this: it gave time meaning, not just as a coordinate in equations, but as the stage for galaxies, life, and stories, a dimension where possibilities unfold and never rewind. Every moment we experience, from the birth of stars to the ticking of a clock, is a footnote to that singular event 13.8 billion years ago, when the universe chose its direction. And somewhere in the answer to why time flows forward lies a deeper truth, not just about how the universe began, but what it means to exist within it. Cosmic inflation has been the gold standard for explaining the universe's early moments, but not everyone is convinced. At the heart of the debate is a simple but damning critique. Is inflation so flexible that it can explain any observation, making it unfalsifiable? Philosopher of science Karl Popper once argued that for a theory to be truly scientific, it must make predictions that could disprove it. Inflation, critics say, fails this test. Need the universe to be smooth. Inflation stretches irregularities flat. Need tiny fluctuations for galaxies to form. Quantum jitters during inflation provide them. The theory's adaptability is so broad that some compare it to a cosmic Rorschach test, seeing whatever you want in the data. The criticism gained traction in 2014 when prominent physicists, including Paul Steinhardt, one of inflation's original architects, published a scathing reassessment. They argued that without clear, unique predictions, inflation isn't a single theory but an umbrella for countless models, many mutually contradictory. Imagine a weather forecast that could retroactively justify sunshine or a hurricane. That's the slippery slope inflation's detractors warn about. Even the apparent smoking gun of primordial gravitational waves detected by the BICEP 2 experiment in 2014 turned out to be cosmic dust, a cautionary tale about confirmation bias. Yet the backlash isn't just philosophical. Alternative models are gaining ground, offering starkly different visions of cosmic origins. Take the bouncing universe scenario, where the Big Bang wasn't a beginning but a rebound from a prior collapse. In this cyclic cosmology, the universe's uniformity isn't ironed out by inflation but inherited from an earlier epoch of slow contraction. No exponential stretching, no quantum fluctuations, just a cosmic pendulum swinging between expansion and collapse. Supporters point out that bouncing models avoid the singularity problem entirely, replacing the Big Bang's infinity-laden starting point with a smoother transition. Then there's emergent gravity, a radical idea that rethinks spacetime itself. Proposed by Eric Verland, it suggests gravity isn't a fundamental force but a side effect of quantum entanglement, like a cosmic illusion. In this framework, the universe's structure emerges from deeper information theoretic principles, rendering inflation unnecessary. It's a long shot, but if evidence mounts, it could upend not just inflation but our understanding of how space and time operate. Even within mainstream cosmology, dissenting voices propose tweaks. String gas cosmology, for instance, replaces inflation with a dense, hot early universe governed by string theory's extra dimensions. Here, the universe's uniformity arises not from rapid stretching but from thermal equilibrium in higher dimensional space. While speculative, it offers testable differences, like distinct patterns in the cosmic microwave background that future telescopes might spot. What's revealing is how these debates mirror scientific revolutions of the past. Just as Einstein's relativity overhauled Newtonian mechanics, today's cosmologists are wrestling with whether inflation is the final word or a placeholder for something deeper. The stakes are high. If inflation falls, so does our best explanation for the universe's structure. Yet that's how science progresses, not by clinging to elegant theories, but by confronting their flaws. Whether inflation survives or yields to a successor, one thing's certain: the universe's origin story is still being written, and the most exciting chapters may lie ahead. The discovery of the Higgs boson in 2012 wasn't just another particle, it was the final piece of a cosmic puzzle half a century in the making. This elusive particle, often called the God particle, is the physical manifestation of the Higgs field, an invisible energy web that permeates all of space. Without it, electrons would zip around at light speed, atoms couldn't form, and the universe as we know it would be a chaotic, structureless void. But here's where it gets even more fascinating. The Higgs field might not just shape the microscopic world, it could have played a starring role in the universe's very first moments, steering the course of cosmic inflation itself. Picture the infant universe, a seething cauldron of energy where the Higgs field hadn't yet settled into its current state. In those first fractions of a second, temperatures were so extreme that the field likely flickered between high and low energy states, like a needle bouncing wildly on a cosmic compass. Then, as the cosmos expanded and cooled, the Higgs field suddenly froze into its stable configuration, a moment physicists call spontaneous symmetry breaking. This transition wasn't gentle. It released an enormous amount of latent energy, potentially fueling inflation's explosive expansion. Some theories suggest the Higgs could even be the inflaton, the hypothetical field responsible for driving that rapid stretching of spacetime. The implications are staggering. If the Higgs field did trigger or influence inflation, it means the same physics that gives particles their mass also determined the large-scale structure of the universe. Those quantum fluctuations during inflation, they might trace back to Higgs field vibrations magnified to cosmic proportions. The galaxies, the cosmic web, even the unevenness in the microwave background could all bear the fingerprints of the Higgs' early behavior. It's as if the universe's grandest structures were encoded in the tiniest vibrations of a single field. Yet mysteries remain. Why did the Higgs field settle at its specific energy level, giving particles precisely the masses we observe? If it had stabilized at a slightly different value, protons might have been too heavy for atoms to form, or electrons too light to bind them. This fine-tuning puzzles physicists, leading some to propose multiverse theories where countless universes have random Higgs values, and we just happen to live in one where the numbers permit complexity. Others speculate about undiscovered particles or forces that guided the Higgs to its current state, like invisible hands shaping cosmic destiny. Experiments at the Large Hadron Collider continue probing these questions, smashing protons together to recreate conditions not seen since the universe's first trillionth of a second. Every collision is a miniature Big Bang, offering glimpses of how the Higgs behaves under extreme energy. Future upgrades could reveal whether the field has hidden properties, extra dimensions, interactions with dark matter, or even connections to the inflaton field. The answers might rewrite not just particle physics but our understanding of cosmic origins. What's breathtaking is how deeply interconnected these scales are. A field that determines why you have mass might also explain why the universe isn't a featureless void. The Higgs isn't just a particle in a lab. It's a bridge between the quantum world and the cosmos, a silent architect that shaped everything from the smallest atoms to the largest galaxy clusters. And as we unravel its secrets, we're not just studying physics, we're reading the universe's autobiography, written in the language of fields and forces. Imagine rewinding the universe like a cosmic film strip, watching galaxies shrink back into clouds of gas, then further, into a seething plasma of particles so hot that atoms couldn't even form. That's exactly what supercomputers are doing today, running simulations so precise they can recreate the universe's evolution from its fiery infancy to the sprawling cosmic web we see now. These aren't just computer games, they're virtual laboratories where scientists test theories about the Big Bang's aftermath, tweaking variables like gravity's strength or dark matter's behavior to see which settings produce a universe that matches our own. One of the most stunning breakthroughs in this field is the Illustris TNG project, a simulation so detailed it can track the formation of individual galaxies across billions of years. The code starts with the universe as a nearly uniform soup of matter and dark matter, then lets physics take over, gravity pulling matter into clumps, gas cooling and collapsing into stars, black holes growing and spewing energy that shapes entire galaxies. The result, a virtual cosmos eerily similar to the real one, complete with spiral galaxies, clusters, and voids. But here's the twist. These simulations reveal that without dark matter's invisible scaffolding, galaxies would be misshapen blobs or fail to form at all. It's like discovering the hidden blueprint of reality. Dark matter isn't the only mystery these simulations tackle. They've also shed light on why the universe looks so lumpy on large scales, why galaxies cluster into filaments and walls with vast empty spaces between them. By comparing simulated data with sky surveys like the Sloan Digital Sky Survey, scientists found that the patterns match only if they include tiny quantum fluctuations from the Big Bang's inflationary phase. It's as if the universe's largest structures were imprinted by subatomic jitters magnified to cosmic proportions. But the real power of these simulations lies in their ability to explore what-if scenarios. What if dark energy were stronger? Simulations show galaxies would be ripped apart before life could arise. What if the initial density fluctuations were smaller? The cosmos would remain a featureless haze. It's like running a million alternate versions of the universe to understand why ours turned out just right. Of course, these digital universes aren't perfect. They rely on approximations, breaking space into grids, modeling star formation with simplified rules, and even the most powerful supercomputers can't simulate every atom. Yet they've already solved puzzles like why some galaxies stop forming stars. Answer: supermassive black holes blast away their gas, and as computing power grows, so does the ambition. Future simulations aim to capture the very first stars, made of pure hydrogen and helium, whose ultraviolet light ripped apart atoms in a process called reionization. The irony is delicious. To understand the universe's past, we're building its future inside machines. These simulations aren't just recreating history, they're testing the limits of our theories, pushing us closer to answering the ultimate question: why does the universe exist as it does? Every line of code, every virtual galaxy, brings us one step nearer to decoding the Big Bang's greatest secrets. The universe seems almost too perfect for life. Every fundamental force, every constant of nature, from the strength of gravity to the charge of an electron, appears precisely calibrated to allow stars, planets, and ultimately, living things to exist. Tweak any of these values even slightly, and the cosmos would be unrecognizable. A bit more gravity, and stars burn out in millions of years instead of billions. A weaker nuclear force, and hydrogen never fuses into helium, leaving the universe dark and lifeless. This eerie precision is what scientists call fine-tuning, and it raises a profound question. Did the Big Bang set the stage for life not just here, but everywhere? One of the most striking examples of cosmic fine-tuning is the production of carbon, the backbone of life as we know it. Inside stars, carbon forms through a rare two-step process called the triple alpha reaction. First, two helium nuclei fuse into beryllium, which usually decays almost instantly. But if a third helium nucleus strikes at just the right moment, it creates carbon. The odds of this happening depend critically on the precise energy levels inside atomic nuclei, levels that, as physicist Fred Hoyle famously predicted, had to be just right for carbon to exist in abundance. When experiments confirmed his prediction, it revealed something astonishing. The laws of physics seem conspiratorially arranged to produce the very element life requires. But carbon isn't the only lucky break. Water, another essential ingredient for life, owes its unique properties to a delicate balance of electrical forces between hydrogen and oxygen. If these forces were even slightly different, water wouldn't expand when it freezes, oceans would solidify from the bottom up, and life might never have gained a foothold. Even the universe's expansion rate plays a role. Too fast, and matter disperses before galaxies can form. Too slow, and gravity collapses everything back into a fiery crunch. The Big Bang's afterglow, the cosmic microwave background, reveals a Goldilocks expansion, not too rapid, not too sluggish, but perfectly tuned for structure to emerge. So is life a cosmic fluke, or is the universe hardwired to produce it? Some scientists argue for the latter, pointing to the sheer number of galaxies, 2 trillion in the observable universe, each hosting billions of stars with their own planets. With odds like that, even rare conditions become statistically inevitable. Others take it further, suggesting that fine-tuning hints at deeper laws we've yet to uncover. Perhaps there's a theory of everything that naturally explains these constants, making life not an accident but an expected outcome. Then there's the Multiverse Hypothesis, which flips the script entirely. If countless universes exist, each with random physical laws, we'd naturally find ourselves in one where conditions permit life. In this view, fine-tuning isn't a puzzle to solve but a selection effect, like a lottery winner marveling at their luck while ignoring the millions of losing tickets. It's a humbling thought. Our universe might be one of countless experiments, most sterile, a few fertile by chance. Yet for all these theories, one fact remains undeniable. The same physics that governs distant quasars and colliding galaxies also crafted the molecules in your cells. The Big Bang didn't just create a universe, it created a universe capable of creating us. Whether by design, accident, or some deeper principle still hidden, the cosmos appears exquisitely primed for life to arise. And if that's true here, it's hard to imagine we're alone in the darkness. One of the biggest mix-ups about the Big Bang is the mental image it conjures, a massive explosion like a cosmic firework bursting outward in space. But here's the twist: the Big Bang wasn't an explosion in space at all. It was the explosive expansion of space itself. Picture this: instead of debris flying through an empty void, imagine the very fabric of reality stretching, carrying galaxies along with it like raisins in a rising loaf of bread. This distinction is crucial because it changes how we understand the universe's birth. There was no center, no edges, just everything, everywhere, expanding all at once. Another common myth, that the Big Bang was a moment of creation happening somewhere out there. In reality, it happened everywhere simultaneously. When astronomers say the universe is expanding, they don't mean it's spreading into some pre-existing emptiness. Space itself is growing, pushing galaxies apart as it stretches. This means if you could rewind time, you wouldn't find a single point where everything began. You'd find the entire universe compressed into an unimaginably hot, dense state, with every location we now observe overlapping in the same tiny volume. Then there's the misconception that the Big Bang explains the absolute beginning of everything. While it describes the universe's evolution from an incredibly hot, dense state, it doesn't, and can't tell us what came before. The laws of physics as we know them break down at the moment of singularity, leaving questions about the true origin shrouded in mystery. Some theories, like loop quantum cosmology or string theories bouncing universes, suggest there might not even be a before in the traditional sense. Time itself could be part of the universe's structure, emerging only after that initial moment. People also often assume the Big Bang was a violent, chaotic event, like a bomb going off. But in the earliest stages, the universe was remarkably smooth. Tiny quantum fluctuations, magnified by inflation, eventually seeded the galaxies and cosmic structures we see today. Without that initial uniformity, the universe might have collapsed back on itself or torn apart too quickly for anything to form. It's as if the cosmos had to be just turbulent enough to create structure, but not so chaotic that it couldn't hold together. Finally, there's the idea that the Big Bang is just a theory, as if it's a wild guess waiting to be disproven. In science, a theory isn't a hunch, it's a well-tested framework supported by overwhelming evidence. The cosmic microwave background, the abundance of light elements, and the observed redshift of galaxies all converge on the same conclusion. Even the distribution of galaxies across the sky matches supercomputer simulations of cosmic evolution. The Big Bang isn't a guess, it's the story written in the stars themselves. Understanding these nuances doesn't just correct misconceptions, it deepens our awe. The universe's beginning wasn't a simple explosion, but a profound transformation of space-time, energy, and matter. And every time we look up at the night sky, we're seeing the aftermath of that extraordinary event still unfolding around us. The Big Bang isn't just a scientific theory, it's the origin story of everything. Every atom in your body, every star in the sky, every galaxy spinning in the void traces back to that single, unfathomable moment. Think about it, the iron in your blood was forged in the heart of a dying star, and that star itself was born from the quantum ripples of inflation, stretched across the cosmos like cosmic breadcrumbs. This isn't just astronomy, it's genealogy on the grandest scale. What's even more astonishing is how far we've come in piecing this story together. A century ago, many scientists believed the universe was static and eternal. Today, we can map the afterglow of creation itself, measure the echoes of gravitational waves from colliding black holes, and simulate the universe's infancy inside supercomputers. Each breakthrough isn't just a new fact, it's a thread in the tapestry of our cosmic identity. Yet for all we've learned, the Big Bang is just the beginning of the mystery. Dark energy's accelerating push, the enigma of dark matter, the question of what, if anything, came before, these aren't just puzzles for physicists. They're invitations for all of us to wonder, to question, to marvel at the fact that we're here at all, in a universe capable of asking these questions. The journey doesn't end here. Telescopes like James Webb are peering deeper into the past than ever before, while quantum experiments and particle colliders recreate conditions unseen since the universe's first trillionth of a second. Every discovery rewrites the story, not just of the cosmos, but of us. Because to understand the universe is to understand our place within it, a fleeting spark in an epic 13.8 billion year saga. So keep looking up, keep asking questions, and remember, when you gaze at the night sky, you're not just seeing distant stars, you're witnessing the legacy of the Big Bang, the ongoing story of a universe still becoming. If you've enjoyed this journey through space and time, let us know in the comments, and don't forget to like and subscribe for more cosmic adventures. The universe is vast, but curiosity is even bigger. Until next time, stay curious.